Alright, hi, I'm Case. I'm gonna be doing number 6. So we have like 2 rods, but like they're different widths, you know? They have different diameters. But there's no space between the things they're attached to. So because of that, it's also heating up. So like it's getting deformed through thermal deformation. Yeah, expansion. So we can say that the deformation from thermal equals the deformation from like the force, like the Pli equation. So we're given all these values for both rods, and we can solve for these values, and adding that up, that's the total deformation in this entire system. So since I just said the total deformation for the thermal side of it is equal to the force side of it, and we're solving for the maximum force we could apply to this, we can just set both sides equal to each other. The thermal for AB and BC equals the force for AB and BC. And using the Pli equation, since they'll have the same force acting on them in the system, you can actually take the P out and just factor it out. And this is what we're solving for. It also gives us the length, it gives us the Young's modulus and the diameter, which you can find the area for, the cross-sectional area. And
what's alpha in this equation?
Alpha is the thermal constant. Like it's given to you. Yeah. So then you just set it equal to each other.
And that's just varies for different
materials.
Yeah. And it does. And then we just solve for P. We just isolate P using this, and then we get P. That's pretty much it. Any questions?
If there was a gap between one of the blocks and then like the wall, our force would still be
that's like the one we did in class.
Yeah, that would be like the one we did in class. Then you can't set these equal to each other. You'd have to
I think you'd have to solve for the deformation before it hits the wall, and then see if it's going to have more force applied after that.
That's when we start cutting and slicing, but here it's like it's much easier because we can just say they're equal. So
yeah, I was very grateful.
Yeah, thank you.
Okay.
Who's up next? Thomas.
I'm Thomas Brandt. This is questions 4 to 5. So we're given this diagram, and the first question asks us to determine the additional tensions in the wires from this applied force. And so first, you should always draw your free body diagram. So we got the reaction forces at A, we have the tensions, and then we have the applied force. The thing that made most sense to me first was to set up a moment about A, so we can cancel out these reaction forces. We don't have to worry about that. That'll give us an equation that's in terms of 2 unknowns. So now we need to find out a way to relate one to the other, which we can do with this strain equation. I did this a couple days ago, so I'm trying to remember how I derived this exactly. If you guys remember, that would help too. But
well, I have a question just going backwards a little bit. So this is when you do the moment, this is when you kind of realize it's statically indeterminate, so you can't, because there's too many unknowns with the statics, so we can't, like this could be a statics problem if we got rid of like, say, that tension right there.
Can you not use forces in the Y in this problem?
I think,
didn't you try that?
I did try that, yeah. It's because if you add in the reaction forces at A, then all of a sudden you got 4 forces in the Y direction.
We don't know AY, right?
Yeah.
My word, you don't want that.
Yeah.
Wow, yeah.
Anyways, what were you saying over here, Thomas?
So we got strain in C is equal to 2 times a length change over 18. 18 is the 10 plus 8. That's the total distance.
Did you ask a question how it was derived or something?
Yeah, I'm trying to remember, because I did this a while ago.
So it's delta L over L. So our L is 18 inches, right?
Yes.
And our delta L is how much it has changed. It's 2 times the length change of EB, remember? Because it's 2 times the length.
Yeah. I remember. Okay. And then, so we can turn that in terms of, you can equate tension to the strain in this problem. So
why can we do that?
It's because strain and stress are proportional. So when you
due to Young's modulus. And then stress is proportional to the force. So we can just like yoink those in.
And the force is tension. So you can kind of like we can skip some
look
steps.
Look at him go.
Yeah.
And then,
is this on?
Yeah, it's on.
Wait, what happened?
Oh, okay.
Oh, I thought it died.
We're
good. And then you can do sigma equals P over A to relate force and.
So technically, if E goes up or if strain goes up, this will go up. This goes up. Force goes up. So you can kind of just equate them like that.
Oh, done. Yeah.
And then
you don't have to do this.
And then when you were talking about the relation with the double, with the 2, like, the proportions. I was thinking about it. The way I thought about it was, this is just a tangent. Sorry to interrupt you.
No, you go.
You can just do a little similar triangle. So like if you think about it, the force right here, if you're pushing, let's put it so they can see. If you're pushing on my arm, so this would be this is the original, right? So there's a similar triangle right here. So this is the original, and then one of them, and then the other one. So these are going to be similar triangles. So the proportion change, the delta L we're calling this. So this is delta L. These delta L's are going to be linear. So this is going to be 1 factor, this is going to be 2 factor, and 3 factor since they're evenly spaced. Anyways, that was the way I thought of it, but continue.
No, that's a good thought.
Yeah, so similar triangles.
And then, so we get this TC equation, we can plug it back into our moment, and we can solve for first our TB unknown. Using that TB, we can then plug it back into this equation we just found and get our TC. And then question 5 is asking, we want the deflection of point D. Point D in this case is here, which is, yeah.
What is the deflection? Sorry.
It's the same thing as your squiggly cobra, the lower, what is that?
Delta
Lowercase-
L, delta L.
Delta L.
Oh, okay,
So it's a
okay.
change in
Length.
which you'll see right here. We have what's this symbol called?
Delta. I think it's a delta.
Delta.
It's
Lowercase
called a
delta.
Yeah.
Delta D is equal to.
Yeah, why'd we start using some of them lowercase and some of them like?
They probably mean different things. So.
Yeah, I don't know.
Why do you call it squiggly cobra? Cobra's
It
already
looks like a cobra.
But a cobra's
It
already
low-key
squiggly.
does.
Look at mine up there. It's like a snake.
This, yeah,
Tell me
that's a cobra.
There's like a naming scheme.
It's just a cobra.
And look at
This is the brand.
There's a
naming scheme.
consistent naming scheme within certain academic circles. And I don't make them.
Get on with it.
Okay, squiggly. Lowercase delta D is equal to. We're using our Pli equation. Remember, P isn't always P. We don't want to use this
use
P.
the flea equation too.
Or Flee.
the same.
However, yeah. So we'll use tension TD. Is that no
B.
TB? That's B.
Yeah, because D is where the points.
We didn't solve for TD. TB times the change in length of right here, which is 10, over the given E, over the given Young's modulus in area for this part, and this stuff's proportional, so we can just multiply this by 3. We don't have to do this like 3 times.
Wait, sorry, was that D or B?
That's a B.
That's B, but delta D is equal to B. Yeah. Okay.
Is that yeah? No,
okay,
so
okay.
because they're we're talking about like how they're proportional, right?
Yeah. Okay.
So
Yeah.
I was confused at
I see
first
what you're
too. And then you should get something of this magnitude in inches.
Thank you so much, Thomas.
Yeah.
Well done.
All right. Thank you. Can we tilt that up a little bit? Oh, that's beautiful. That's beautiful. All right. So here we're given I don't even know what you call this, just like a
Hanging
multi-dimensional hanging mass
Hanging
rod
pipe pole
system.
Well said.
In some academic circles. Okay, so this is
I'd
definitely not...
say a composite rod with ends restrained. Oh, wait, no, wrong question.
Okay,
my marker?
it's a composite rod with one end restrained. So this is not proportional at all, as you can see, but they give us the lengths and the applied forces.
It's a step shaft. I'm sorry.
A step shaft. So the first thing they're asking is for the deformation in segment AB. So what we're going to do is make a nice little cut. So,
Would you mind drawing that on the? Oh, he grabbed. Wait, hold on. I want to see like on the diagram where you cut it because I was confused about this at first.
So we're going to make a little cut right here. So now it's important to note that this cut is right on that 120 mark. And so the key with the cuts is, I think it'll make more sense actually if I start actually explaining the second problem where they're asking for the deformation at D.
Okay.
So D is they're asking for the total deformation of the whole, what was this called?
The step shaft.
They're asking for the deformation of the whole step shaft. So essentially, obviously that seems pretty simple, but since there's forces applied at different points, like there's a force applied at B, there's a force applied at C, and the step shaft has different, I think it's all the same material, but it has different diameters, different areas, like cross section is going to be different. So we have to do it modularly. And that's how we're going to decide where to make our cuts, is where the force is going to change. So that's the conceptual way that I was thinking about it. So if we were looking at D, we're going to end up using our answer from AB, which is why I'm actually going to start talking about D, and then I'll get back into AB. But, so we're trying to find the total deformation of the whole thingy. I'm not even going to call it whatever, but excuse my language, I'm sorry. So we're looking for the deformation at D. So if you want to work backwards, you can do that. That kind of makes more sense intuitively to me. But you can separate this into essentially 3 different systems. So we have 1, 2, 3. And this is every time the force changes. So every time a different force is applied, we're going to make a little bit of a cut.
Did you cut B and C there for that one? Did you isolate just that opponent?
Yeah, so this I did, yeah. So I isolated just this little segment.
Okay, but you still kept the forces, I see, from D?
Yeah, so we'll get into that. So I'm going to start at the bottom with CD here. So I've cut off C. And so the way that I was doing it was, you can start from the top or the bottom, but if you cut it off, this is now independent, so I'm just going to ignore, like pretend that this is solid foundation. So we're going to ignore any applied forces at C when we do our little cut. And the reason I'm doing that is so that we can isolate the CD component. I think this took a little bit to conceptually understand of what forces to include and what not to include.
Yeah.
But that's the way I was thinking about it. So like if we look at our cut on AB, we cut right here. But you'll notice I did include the 120 this time. So that's because here I'm applying this as locked in. And so the 120 is obviously going to be affecting this segment, right? And then here, this 75 is not affecting that segment because I decided that this was the like solid foundation.
So you don't cut and look at the top, you cut and look at the bottom?
Yeah.
Why is that?
Yeah. I think that's just a conceptual way that you can do it because we're working down towards point D and finding the total deformation.
That's why in the in-class example, it was coming from the floor upward. So
it was a little bit different.
Yeah.
Yeah.
Because they're finding different things?
Yeah.
So anyways, the key is once you make all of your cuts, as you can see we have them here, you can draw a free body diagram. And I think that's really the hardest part. Once you have those, you can solve for the internal forces and plug in said internal force. So right here I've solved for the internal force FAB, 5 kilonewtons, plugged it in to our Pli equation.
You find that using delta F, right? Fy?
Yes, sigma Fy.
Or sigma Fy?
I've been calling it delta this whole time,
always
and I
say
think
delta.
I spread that to all of you
Delta
guys.
Fy.
I think that's my fault. So yeah, we plug that in using our sigma Fy. We're going to get 5 kilonewtons multiplied by 1,000, blah, 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 unit change. Yeah, and I think most of this other stuff was given. Just make sure you're careful of which cross-sectional area you're dealing with. And then you're going to take all of these deformations across their respective cuts and add them all together, and you'll get your total deformation.
Wait. Okay, yeah. No, I think that makes sense.
I got a conceptual question.
Okay.
It's like trying to relate things to what we've learned in like 30A.
Yeah.
But when you're making the cuts, is this the same process as what we did with the like? Is this just method of separation, or is this like a different?
I see what you're saying. I think it's a little bit different, but it's kind of also the same because here we're cutting where the force changes. So if you think about it,
internal forces. So
yeah. So if you think about it, if there was no externally applied forces on points B and C, we could just deal with this all as one kind of system, right? We might have to separate it into the diameter change, but essentially what you're thinking about is because we can't account for all of these changes, like compoundedly. So we have to break it up into smaller doable functions that we can plug into our Pli equation. Because either the cross-sectional area is changing or the applied force is changing, that's when you want to make your cut. So I think if you just look at it, and then the hard part is then what forces to put. But if you just work top to bottom or bottom up at whatever seems intuitively easy for you, it also depends on the problem.
Okay.
That's going to help make that a lot clearer. And then when we're working with trusses, you're kind of cutting along the unknowns to separate it into a different system. So I think it's a similar foundation, but a little bit different method of where and when and where you're cutting, but very similar, good connection.
Okay. Cool.
All right, you want to pass it on?
Yeah.
All right.
Okay. So, gonna show you number 3. I didn't draw it, so I'll just show you it. This is the diagram of what we're working with, so just keep this in mind. It's a concrete beam with 6 steel support beams within it.
It's a great drawing.
I made that myself. So, with that,
Is that on
in
Fusion?
mind,
SolidWorks.
for this problem, we're trying to find the maximum centric force that can be applied onto it, and we're given some givens to work with that. So, the first thing we're going to do Sorry, guys. Is this deformation, deflection, or
This
like
is
I
the
get them
total
all?
length change. So that's
Length.
your
I'll call it like elongation.
yeah, that's delta L. It's the same thing as delta L.
Okay, yeah.
Which is the same thing as deflection.
Yeah, okay, let's call it delta. So we're gonna calculate that for the concrete and the steel. So keep these in mind, both very small numbers. But this one is smaller, so that one's more important because we're trying to find the maximum. We gotta find which one breaks first,
So
essentially.
you're saying that one fails first? essentially.
Yeah, the concrete will fail
Okay.
before the steel, which makes sense if you think about the material properties.
Okay.
So
Even though it's so much bigger, you think it'd fail first?
Science does not always matter.
Oh, okay, you're right. Okay. Keep on
Because
going.
it's
my
more a
bad.
matter of the maximum stress which they gave us, and the Young's modulus, which is also given.
yeah, so I guess
Respective
that's more
properties.
off the actual material, like not taking
It's like
into-
internal stuff, even though it looks bigger.
Yeah,
it's
yeah,
like
we're not
internal.
actually like taking in the actual thing. I don't know.
There you go, bro.
So from then we're gonna try to find the stress. Yeah, stress. That's stress. There's too
That's
many.
strain.
No, because no,
Yeah,
it's
it's
not. So we'll isolate for stress, and we'll get 11,890 psi, give or take.
I mean,
We're fooling around.
can you please finish?
Yeah, yeah. So from there, we can actually find our force. So we'll calculate it for the concrete and steel. And these are, so we just do sigma equals P over A, solving for P. The difference between these two is going back to here.
Sorry, what is 6 pi? Is it just pi? Pi squared?
Yeah. No, we have 6 pi because there's 6 steel beams within it.
Oh, okay.
So
yeah,
we
that
just
makes
multiply by 6 to
I
take
think I
it.
kept forgetting to do that, and that was throwing me off.
Yeah, I was multiplying by 5 for some reason.
Oh, 'cause
Because
it was the
I
length.
thought the length was what we were taking.
And this is the square surface of the concrete beam minus
Yeah,
the...
so the concrete has an area of 100, and then we're just subtracting out the steel beams.
Okay.
Okay.
So you'll get those, and you'll add them together because they're both, it's not just like even though it fails first, it's not just the concrete that we need to worry about.
Yeah.
Because they're both
Okay.
supporting each other. So you'll find both of those values, add them up, divide by 1,000 because we're talking about kips. I don't even think you can see that. Yeah, you'll get 185.6 kips. That's its failing point.
Well done.
All right.
Thank you. Do you have any questions, Sam?
I think that makes.
You want to make an appearance? All right.
All right. Thank you, ladies and gentlemen.